All right, I'm going to talk about probabilistic modeling and Bayesian inference. I'm going to steal a little bit of Bernard's topic, which is just to introduce, in my view, what is machine learning. Very, very quickly, I don't want to bore anybody here, but just very quickly, there are lots of related terms. You know, you can pick your favorite one here, like data science, or did I put deep learning? No, I haven't put deep learning on there. You can pick your favorite term. All of these are related terms. They go in and out of fashion. But the really good news is that the concepts, the basic theory, the ideas persist over many, many decades. And so there's a rich and long history of people trying to get computers to learn from data. And that history comes from lots and lots of different fields, lots of disciplines. It's not owned by computer scientists. There are people in engineering and signal processing, information theory that have thought about these things, adaptive control theory. It's obviously relevant to people in statistics. We get a lot of inspiration from cognitive science and psychology, and a lot of really good ideas actually came originally from those fields and then got formalized by people in computer science and statistics. We get a lot of inspirations from computational neuroscience. It even relates to ideas in economics, like decision theory, what do rational agents do, fields of operations research, and so on. So there are lots of different fields involved, but as I said, the same set of ideas and mathematical tools have been reinvented across many of these fields, although maybe with different emphases. So for me, machine learning is an interdisciplinary field focusing on both the mathematical foundations and practical applications of systems that learn from data. Okay, so let's contrast two views of machine learning. So one of the views is that machine learning is a toolbox of methods for processing data. You have your data. You download some software, you stick it in this thing, then you stick it in that thing, and then you stick it in that thing, and then you get some result at the end. And of course, I'm sort of caricaturing that, but I think that that's actually the largest use case of machine learning out there in the real world, certainly in industry. Now, there's nothing wrong with that, and by the end of that process, you have to have some understanding of the properties of that process. So you'd like to choose methods to stick your data into that have either good theoretical properties, so there's a lot of interesting learning theory you can do on these processes, or that have good empirical performance. And ultimately, you're interested in making predictions and making decisions based on data. The kind of view that I like to take is machine learning as it's sort of a modeling view. Machine learning as the science of learning models from data. And in practice, it ends up involving the following. You've got your data, you define a space of possible models, then you learn the parameters and structure of those models from the data, and then you make predictions and decisions and so on. And again, you know, that's not guaranteed to do well. You need to do some theory to understand that, and you need to evaluate empirical performance to make sure that you're doing something sensible. So let's look at this modeling view of machine learning. And this is going to be the topic of my lectures, my sort of roughly 3 lectures. So the view that we're going to take is machine learning as probabilistic modeling. So what's a model? A model is a description of possible data that you could observe. Okay, so the only way I'm going to be able to tell if a model is good is if its predictions of possible data are similar to data that I actually end up observing. Now, if I'm trying to build models so as to make predictions and forecasts, then I better have some uncertainty, okay? Because, you know, given the data that I obtain, my training data, if I'm trying to make some statements about data I haven't observed yet, I'm necessarily going to be uncertain about the data I haven't observed yet. Like, let's say, the label of a new data point or something like that. Okay? So we're going to use the mathematics of probability theory to express all the forms of uncertainty that we have in our model, the structure of the model, the parameters of the model, and the noise processes that might be involved. And then the good news is that we can use just basically the same mathematics of probability theory, something that used to be called inverse probability or Bayesian inference, as it's called now, to infer unknown quantities, adapt our models, make predictions, and learn from data. So here is Bayes' rule. So the way I'm gonna do it with words. So imagine you're a scientist, okay, and what you're trying to do is reason about hypotheses in some scientific area, and you're able to do an experiment and collect some data. Now, before you do the experiment, before you look at the data from the experiment, you may have certain hypotheses for what might be going on, and you have some beliefs about those hypotheses. So you're going to use probability theory to represent how confident you are about each of the different hypotheses. That's what's called the prior. And then each of those hypotheses, to be a well-formed hypothesis, it has to be able to make some probabilistic forecasts about the experimental data that you are going to collect. And so each of the hypotheses produces what's called the likelihood, the probability of the data given the hypothesis. And then you multiply the prior times the likelihood, and you renormalize, this is a normalization constant here, to get what you've learned about the hypotheses. This is the posterior over the hypotheses given the data. Now, at this high level, Bayes' rule tells us how to do inference about hypotheses from data. It's an interesting concept because, actually there's some interesting arguments for how aspects of human perception are well modeled by Bayesian inference as well. Like when we open our eyes, our retina gets data, and we may have some expectations about what we see, what we would expect to see in this room, like, people, not elephants and giraffes or something like that. And we open our eyes, and then our brain somehow processes the data, combines them with our expectations, and produces a hypothesis about what's out there. Okay, so learning and prediction can be seen as forms of inference. And Bayes' rule is due to Reverend Thomas Bayes, who lived in the 1700s, and this is not a portrait of him, just so you all know. We all thought it was a portrait of him for a very long time. Everybody uses this because we have no other portrait. We don't know who this poor guy is, actually. But it's not him. And the way we know that it's not him is that after many, many years, somebody who was an expert, you see, Thomas Bayes was a nonconformist English minister, and it turns out nonconformist ministers in the 1700s were never dressed like this. Okay, so that's not Thomas Bayes. But we're going to use it anyway, and don't tell anybody else. Okay, all right, so here's the plan. I'm going to introduce some foundations and talk about intractability, then some approximation tools, then advanced topics, limitations, and discussion. That's just lecture 1, okay? And then there's all sorts of other good stuff. This is the more detailed plan for lecture 1, in case you were tempted to ask me questions. The more you ask me questions, the less you get to find out all these interesting things. No, seriously, actually, I do enjoy questions, and if I find that it's going too slowly, I'll just speed up at the end, so it's okay. And you won't understand anything, but you can watch the video afterwards in slow motion, and then it'll be okay. All right, so let's introduce some foundations. All right, let's talk about really simple things. Simple things, linear classification. This is linear classification. We have some data. The key ingredients are we have data. The data are pairs of x's and y's. Y's are some class labels. Let's consider binary classes. The data might look like this. Our model might be a model of some linear decision boundary, which in math you would write like this. This is a hard linear decision boundary. It's a really stupid model, but whatever. Let's put it up here anyway. It just says the probability of being in class 1 is 1 if you're on one side of the class, and is 0 otherwise. So we have ways of making this better, but we start from here. This model has parameters. The parameters of this model are the coefficients that define this linear boundary. And the goal of learning is to infer these parameters from the data so as to predict future labels. Y's for new x's given your training data. Canonical problem number 1, linear classification. Canonical problem number 2, polynomial regression. Now your data is pairs of x's and y's, these red dots. This is y, this is x. Our model is going to be a polynomial, say an mth order polynomial. Y is going to be that polynomial with some noise. The parameters of that model are the coefficients of the polynomial and the variance of the noise. And our goal is to infer the parameters from the data to predict future outputs, future Y's given the data X and maybe the order of the polynomial we've assumed. Okay? Canonical problem 3. You can view this problem in two different ways. You can think of it as clustering with a Gaussian mixture model, or you can think of it as density estimation, estimating a density with a bunch of Gaussians. So this is what's sometimes called an unsupervised learning problem. We have some data. Our data is just points, these blue dots, in some d dimensions. Here d equals 2, obviously. Our model is that the data was drawn by a mixture of m, here m equals 6, presumably, Gaussians, where these pi i's correspond to the relative mass of each of the Gaussians, and each of the Gaussians, pi has some mean mu I, that center location, and some covariance matrix here depicted as an ellipse for the one standard deviation ellipse. Okay? So this has data, a model, parameters are the parameters of the Gaussians and the mixing coefficients here, these pi's. And again, our goal is to infer parameters from the data, predict the density, and perhaps maybe infer which points belong to the same cluster. Okay, we have some queries on this data we could make. All right, so that's the general framework. Those are 3 canonical problems. We could go through many, many other such problems. And the key ingredients they all have is there's always got to be data, and there's often a model. That model has some parameters, and we want to do something. We want to make some sort of predictions based on those parameters. And so the Bayesian framework, the reason it's conceptually nice is that it's incredibly simple. It just says there are 2 rules. You just need to know those 2 rules and apply them wherever you can. The 2 rules are the 2 basic rules of probability theory called the sum rule and the product rule. The sum rule is that the probability of some variable x is the sum over y of the joint probability of x and y. If y is continuous, then we will replace the sum with the appropriate integral. Okay? The product rule says the joint probability of x and y is the probability of x times the probability of y given x, or the other way around, probability of y times the probability of x given y. Now, this sounds a bit boring and elementary until maybe we start doing something with it. We replace x's and y's by the things that we observe and the things that we don't know. In particular, using the sum rule and the product rule, we can get as a corollary Bayes' rule. Here is Bayes' rule. And I've replaced the x's and y's by d to represent, just like in my previous slides, the data that I've observed. This is the thing that's given to me. Theta, the parameters of the model that are unknown. And I've conditioned everything on m, some basic assumptions, some structure of the model that we've assumed. And we'll talk in literally a minute about what to do with m as well. All right, so now this equation, which is Bayes' rule, which is a corollary of the sum and product rule, tells me that if I want to learn the parameters of a model, I start out with a prior, and the prior represents the range of possible sensible parameters that that model could take. Okay? If I have a model, let's say I have a linear regression, and I have a slope parameter, the steepness of that line. Now, if I say, a priori, I believe my slope could range between plus and minus 1, that's a different model from a linear regression model which says, a priori, I believe my slope could range between plus and minus 1 million. Okay? Those are different models. Different models correspond to making different prior assumptions. And specifying those ranges, instead of specifying them as sets, we're going to use probability distributions, because we might want to have kind of smooth, gradual representations of our beliefs about what sensible values might be. And sets are a really bad idea, because a set says there's 0 probability of being outside the set. And that's too dogmatic, because your data might just want to be outside that set. Okay? All right, so we're going to use probabilities to represent our sets of sensible parameters. That's the prior. Then this is the likelihood, which many of you are familiar with, I'm sure. We multiply the prior by the likelihood. We get the posterior. Aha, that's learning. That's everything we've learned about the parameters given the data as a corollary of sum and product rule. The normalization term here is super interesting. This is called the marginal likelihood. And I'll talk about this for a couple of slides. Now, when it comes to prediction, what do? Well, when in doubt, look at the sum and product rule. Prediction is predicting some unobserved quantity x given the data and my model assumptions. And by the sum and product rule, that involves an integral over all possible parameters of the predictions that each of my parameters makes. Each of my parameters makes some probabilistic forecasts weighted by the posterior probabilities over those parameters that I've computed here. Okay? It's a little bit like if you run the weather service and you have a staff of 20 weather predictors, you take each of their forecasts. I mean, this is not how weather services run, probably. But you take each of their forecasts. Each of them says, oh, you know, the probability of rain is this much. And you weight them by how good they've been in the past. And that's what the posterior does. It's a natural ensembling method. And then what you get is a probabilistic forecast for, you know, how much it's going to rain tomorrow or whatever. Okay? Then for model comparison, we apply the same idea at the level of models. These are, M might represent how many clusters do I have, what order polynomial I have, et cetera, et cetera. I'll give examples of that. And this quantity here, the marginal likelihood, is very interesting because it captures some notion of complexity, which I'll talk about. Now, note, where is the optimization rule? Can somebody find the optimization rule? There is no optimization rule in probability theory, okay? Nothing in this probabilistic framework is telling us to go and optimize any parameters. So forget all that optimization that you've learned. No, I'm kidding. Optimization is really useful. Don't forget all that optimization. It's really useful. It just doesn't follow from the general probabilistic framework. So how does a Bayesian view optimization? Okay? Well, we view it in two ways. One of them is that optimization is often a really crude but, you know, useful approximation to doing integrals. So rather than doing an integral, I pick the highest point and I take the value that the highest point is predicting. So optimization is an approximation to integration. That's one view of optimization, one use of optimization. The other use of optimization comes in decision theory. If I've done my Bayesian inference and now I'm trying to make a decision to minimize some expected loss, that is an optimization problem. So Bayesian inference involves no optimization except as an approximation. Bayesian decision theory does involve optimization. Okay? All right, so here is a very toy example. Just to make sure everybody's on the same page, imagine you have some data, these blue dots, and you're trying to fit a model. Your model here might be a multivariate Gaussian. The parameters of the model are the mean and the covariance matrix of the Gaussian, here 1 and 2 standard deviation ellipses for that. And Bayesian inference would say, get a probability distribution over the mean and covariance that's somehow coherent with this data. Okay? Obviously, that's a really bad Gaussian for that data, by the way. That's just an example of a low likelihood Gaussian. Okay. Any questions at this point? Opening up the dragon's den. Okay. Well, the good news is that's it. That's all you really need to know. Okay, it's quite straightforward. You think of some space of models, you do the sum and product rule. You go home. All right? And it's amazing how many problems in machine learning can be tackled in that way. Now, do you have any questions? Yes? Yes?
Wouldn't you have chosen the parameters when you came up with the model?
Chosen the parameters, what do you mean? No. Okay, the Bayesian philosophy is the following. There's knowns and unknowns, and I'm not going to quote Rumsfeld here. There's just knowns and unknowns. The only known is the data, okay? Everything else is unknown. Now, the parameters of my model are unknown. My model structure is unknown. I'm going to have to make some assumptions. So I'm going to say I'm going to look in the space of models of this particular kind. I'm going to be explicit about my assumptions by writing down probability distributions over all of the unknowns that I might have. The structure of my model, the parameters of my model, etc. And then I don't choose a parameter. I average over parameters. It's like an ensemble method if you're familiar with ensemble methods. The sum and product rules say you should average over parameters because you're not sure, right? All you're sure about is the data. Even that, sometimes you're not sure about. But anyway, let's assume you're sure about the data. And then everything else that you don't know, you average over. It's the ultimate hedging your bets kind of thing. Okay, so that's it. What's next? The barbecue or another coffee break, maybe? No. Okay, there are other things to it, all right? Otherwise, they wouldn't have scheduled me for 4.5 hours or something like that. Okay, maybe 4 hours. Well, here are some questions you could have asked if you were paying attention. No, I'm sure you're paying attention, but here are some questions you could have asked if you were less polite. So what motivates this Bayesian framework? Where do these priors come from? How do we do these integrals? Let's try to answer these questions. Okay, so one way of motivating these frameworks is to throw away probability theory and start to think about questions in artificial intelligence. Okay, so here's a question in artificial intelligence. Of course, we all know that involves robots. You're building an artificially intelligent system, and you want it to behave intelligently, and you want it to have beliefs about what's in its world. Like, if it's trying to navigate around this room, it should have beliefs about where the door is, where the walls are, where the small children are, so it doesn't trip over them, etc. Okay? And so the question is, how do you represent beliefs about propositions in the world in the brain, in the mathematical computational brain of the robot? And what we want to do is we want to represent strength of belief numerically. Yes?
I think we have a question from the observation launch.
Aha. They're not as polite. Speak up.
Yes, we can hear you.
It's a Morse code, I think. Okay.
Yours?
Yes.
Yes?
Yes, voice. Is there a question? Because I'm getting nervous about this.
Hello?
Yes, hello.
Okay, great. So the question is about your... Can you two previous slides, please?
That's it?
One more.
Yes.
Actually not here, but anyway.
Another one. Here, maybe this one.
Yeah, that's the one.
Okay.
Yeah. So at the end, the last equation has some kind of integration over parameter, but the equation before doesn't have it. And I'm a bit wondering, what does m exactly represent? It's a bit vague that there is a m, there is a theta, and I cannot quite connect them to each other. And
Okay, good question. Yes, good question. I'm going to give a concrete example. Theta, let's say you have a mixture of Gaussians, okay? In a mixture of Gaussians, I'm going to show you a picture. I chose my notation carefully. I've spent years working on these slides. So I chose M here, okay, to represent the number of mixture components, all right? So for example, in this situation, the parameters of the model might be the means and covariances of the Gaussians and their mixing coefficients. And a structural parameter of my model might be how many components M should I have? Should I have 6 Gaussians for this data, or 3, or 5, or 17? Now, conceptually, you're right that both of them are unknown. And so really, there's nothing wrong with this equation, because remember, this equation is analogous to this equation. Okay? It's just Bayes' rule. Follows from the sum and product rule. Conceptually, here in the prediction equation, this is the predictions for a particular M, for a particular number of components, let's say, 6 Gaussian components. And if I really wanted to do the averaging, I should be averaging over M weighted by this equation. And that, I could have written that equation, but that would be too many equations on one slide. Okay? The examples will be clear later as well. I'll give more examples of M and theta and how they might be used differently. Conceptually, they're both unknowns. Okay? Yes? Question?
Theta should depend on M, right? Like the dimensional theta.
Yeah, in general, theta depends on M. And that's sort of notationally, you could make, here, all of these equations are conditioned on the same M. So I didn't make that distinction. Yes? Okay. So, here are the questions. So let's go back to building our robot. We want our robot to have strength of beliefs numerically represented in its brain, and we want to know what mathematical rules it should use for updating its beliefs and manipulating its beliefs. Okay? So now there's a very nice bit of theory going back to Cox, 1946, which is very nicely explained by Edwin James in his 1996 book. Which goes as follows. Let's say we use B of x to represent the strength of belief or plausibility in some proposition x. Okay? Like, there's a door over there or something like that. Now, we're going to say B of x goes between 0 and 1, where 0 means that x is definitely not true, and 1 means that x is definitely true. Right? X is now not a variable, it's a logical statement. Think of it that way. And we're going to use B of x given y to represent the strength of belief that x is true given that we know that y is true. Now, what the Cox axioms tell us, well, the Cox axioms are the following desiderata, things that we want from strength of beliefs. We want strength of belief to be represented by some real numbers between 0 and 1. We want some qualitative correspondence with common sense, and we could go into this in more detail. And we want some form of consistency. So if a conclusion can be reasoned in several ways, then each should lead to the same answer. And you must take into account all the available evidence. You can't arbitrarily decide to throw away evidence. And equivalent states of knowledge should be represented equivalently with the sort of unique belief assignments. The consequence of this is that belief functions, these strengths of belief, must satisfy the rules of probability theory, including sum rule, product rule, and their corollary Bayes rule. In other words, if I'm trying to do something purely subjective, which is representing beliefs of an artificial system, then probability theory, like in natural language, is a good way of talking about those beliefs. Another argument that comes from gambling or economics is what's called the Dutch book theorem, which I think goes back to Definetti in the 1930s. It says, assume you'll be willing to accept bets with odds proportional to the strength of your beliefs. So again, you have beliefs, and you're a gambling person. So you're going to accept some bets. And what does it mean? Well, the strength of belief is going to represent the odds of a bet that you'd be willing to accept. So if your belief in something is 0.9, like, that Greece will accept the package that's being put towards them by their, by the Troika right now. If your belief is 0.9, then you'd be willing to accept a bet which allows you to win $2 if X is true, and where you lose $9 if X is false. Okay? So this gambling thing is to calibrate your strength of beliefs in various things. And now, unless your beliefs satisfy the rules of probability theory, including Bayes' rule, then there exists a set of simultaneous bets that you would accept, which would be guaranteed to lose you money no matter what the outcome. So it's not about whether you're right or wrong, it's about whether you're consistent, whether you're subject to arbitrage, as some people call it. The only way to guard against these Dutch books is to ensure that your beliefs are coherent. In other words, they satisfy the rules of probability theory. So here's another bit of theory that's relevant to this Bayesian framework. So how does it relate? What happens when you have a lot of data? There's this asymptotic certainty results, which loosely speaking, careful with the regularity conditions, these are just sketches of the theory, but loosely speaking what you have is that assume you have a data set dn with n data points, and it was generated from some true theta star. Then under some regularity conditions, as long as you put prior mass around theta star that's strictly positive, so in other words, as long as you didn't say theta star was impossible under your prior, then in the limit, your posterior probability will converge to a delta function around theta star. So that's a very comforting thing. And it also tells us, don't be too dogmatic. Don't give zero probability to regions of theta space, because that's the only way you can guarantee to converging to the right thing. Now, in the unrealizable case, where the data was generated from some distribution which cannot be modeled by any theta, then the posterior will converge to a delta function at theta hat, where theta hat minimizes the Kullback-Leibler divergence, if you're familiar with that, between the true distribution, P star of x, and P of x given theta. And in fact, that's equivalent to the theta hat that maximizes the likelihood. So in the asymptotic limit, in the worst case, you'll converge to the maximum likelihood. Then there is another interesting result, which is called asymptotic consensus, which says consider two Bayesians with different priors. That's generally going to be the case. Different modeling assumptions come in. There might be somewhat different priors. Call them P1 and P2 of theta. But they observe the same data. What happens then? Well, assume both Bayesians agree on the set of possible and impossible values of theta. And that's sort of important. The priors are different, but the sets that are given non-zero probability density are going to be the same. Okay? Then in the limit of n going to infinity, the posteriors P1 and P2 will converge in uniform distance between distributions. So let me show you this through a quick demo. Just because it's fun to sort of see this. So we have a situation where we have learner A, which is learning about a coin toss and has uniform prior over the probability the coin will come out heads, and learner B, which has a probability that's more centered around 0.5. Two different priors. And then they observe coin tosses. So one coin toss comes in, heads. So learner A's posterior, given the data, now looks like this. It's the prior times the likelihood. The likelihood is a linear function. So the posterior looks like a linear function, shifted towards 1, because heads corresponds to the 1 side, tails corresponds to the 0 side. And learner B shifted a little bit towards 1, if you noticed. Okay? Now we keep going, observing heads and tails. So that was a tail, tail, head, 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 tail, 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 head, etc. Okay? So what's going on? We've now observed a whole bunch of coin tosses. And what do you notice? This is asymptotic consensus at play. Learner A and learner B are converging to very similar distributions. Okay? And what do you think the true value of theta was in this example? 0.6. Actually, I think that's right. So they're converging. They're going to converge to around 0.6. Okay? Any questions about that? Yep.
This has some of the flavor of Alman's agree to disagree theorem. I wonder if it's in some way equivalent.
I'm not familiar with that, I'm sad to say.
So it's a theorem in decision theory which says that basically that people with different priors and access to the same information, if they're rational in a Bayesian sense, must end up with the same posterior. But I don't think it has any of the sort of limit asymptotic arguments that other figures.
It might be a restatement of the same thing in decision theory, yeah. I mean, the great thing about this stuff is that it's been rediscovered in many different places, and people who've thought about foundations of probability have thought quite deeply about this. Yeah, so you're right, that might actually be the same thing.
I think the concept of the theorem is a little bit different. It's what they believe about each other rather
Right,
than
yes,
the
yeah, that's
world.
Yeah.
It's not quite the same.
Okay, you know more than I do. Yep.
Does it mean basically that if we have loads of data, it doesn't matter on the prior?
That's a great question, and I will come back to it later. Yeah. So it means that if we have loads of data and we don't have a lot of parameters, 60 million is a lot of parameters, okay? If we have loads of data and we don't have a lot of parameters, then we'll converge to something. And it doesn't matter what our prior was, as long as it wasn't stupid. Yeah.
Could you elaborate a little bit on the type of convergence? You said it's uniform convergence for distributions. How does it compare to other kinds of convergence?
It's what I had here. It's uniform distance between distributions in this soup norm over sets. But you know, there is a lot of theory involved here. There are lots of different things. So I mean, I don't want to go into it in detail because it's not sort of the main thing. Yep.
When I look at the posterior, does it depend in which order I observe the data?
No.
No matter what the prior is and my distribution?
Well, unless you had a model in which the order was being modeled. Okay. So here the assumption was that the coin tosses were Bernoulli draws from some unknown parameter Q. Okay? And because of that assumption, by the likelihood principle, it should not depend on the order. And Bayesian learning is inherently online in that setting. So actually prior and posterior are not different things. The posterior at one step is the prior for the next data point. And so we iterate. Okay? So there's no magical sort of, okay, we have to start somewhere by writing down some assumptions. But then after that, it's all just updates of your beliefs.
So, but it also doesn't matter whether I do the update in one step, like I have 50 observations.
Yeah, you would get exactly the same result, and that's by the Cox axioms that's required. Because otherwise you're not coherent. Then you're depending on something arbitrary. Yes, question from the... Yep. I'm ready.
So, do you hear me?
Yes.
Can you hear me?
Yes.
Yeah, good. My question is, does this theorem hold whatever the model? So, for example, if you have the wrong model, would this theorem still hold?
Yes. With
So
caveats. Okay. This theorem holds in finite dimensional parameter spaces, as far as I know. It's harder to write theorems like this in infinite dimensional parameter spaces. But there's no statement about right and wrong models.
Okay, because for example, in the example you gave, so you had this coin toss and you had actually chosen the wrong model, but you just did not know the parameter. The question would be, so in reality, what you have is you don't know the model actually
Stop.
generated it.
I didn't choose the wrong model. I chose both learner A and learner B. Let's be clear. Okay. This comes to the question of what's right and wrong. Okay? Both learner A and learner B give probability density to all values of Q between 0 and 1. Okay?
Yes, but I mean, what your data generating, what generates your model, your data is actually something that where this theta has actually some
some value.
real, some real value for this theta.
Okay, this is a beautiful misunderstanding of Bayesian statistics, which is very common even among very senior people. So let me explain it. It's not that the Bayesian thinks that theta is a random thing, okay? The Bayesian says, I don't know what theta is. There might be some value. Okay, let me give you an example. Let's do Bayesian inference on the mass of the moon, okay? By some definition, there is some mass of the moon. It is a number. I just don't know what it is. So I'm going to say it's between the mass of an apple and the mass of the sun with a uniform distribution. Okay, because I'm stupid and I don't know anything about astronomy. That's my prior. And now that's actually not such a bad prior, because the moment I start making a couple of observations, that prior is going to start concentrating on much more reasonable values. Okay? So it's not that we're assuming that theta is random. And therefore, if theta is fixed, our models are always wrong. It's just that theta is not known. Okay?
But that's not it's not my point. Suppose that in your example, your theta would change at each experience. So you would at each experience choose another theta.
Okay.
And you are trying to infer theta that has just no meaning actually in the process that you are trying to.
Okay, I'm glad I got to answer the other question, which was not your question, because I made a point. But your actual question is quite interesting. If my theta was randomly changing at every time step, or let's say it was drifting slowly, like the coin was wearing over time or something like that. These are real things that could happen, right? Then clearly this is not the right model. And that's a situation where I've actually, in a larger space of models, I've put 0 probability mass on any of those models where theta is changing, okay? So this is why we need to be very careful when we define our models to allow for a lot of different kinds of uncertainty and change. Like, for example, there might be serial autocorrelation between the coin tosses, and I didn't account for that. The parameter might be drifting over time, and I didn't account for that, et cetera, et cetera. Yep?
How does the rate of convergence depend on the prior? And it's related to convexity somehow, in the sense that it seems like there's something convex happening here?
Yeah, no, there is a lot of theory on how the rate of convergence depends on the prior, but I'm not an expert. And essentially, there is sort of a divide between parametric and non-parametric models. And in parametric models, essentially, your rate of convergence is near optimal, basically. In non-parametric models, things can go horribly wrong, and there's a big literature on that. Okay, let me move on. Let's see how I'm doing on time.
45 minutes.
Sorry?
45 minutes.
45 minutes left. Is that right? Okay. I thought for a second I have 15 minutes left. But
No.
okay, that's good. All right. Okay. Okay, so that's asymptotic consensus. Here is this coin toss demo again. I won't go through it, but this is if you want to think about these slides offline. You could try to answer these questions, okay, and then try to discuss amongst yourselves, okay. Now let me talk about model selection, and this is an important topic, or model comparison in general, is really a fundamental topic in machine learning and statistics. So we have some data, consider a regression problem, and we're trying to predict y from x, and we could fit, let's consider polynomials for now, constant, linear, quadratic, cubic, quartic, quintic, and whatever these things are called, okay? Now, clearly, at this point, the 7th order polynomial, if I have 8 data points, I can perfectly fit those 8 data points with the 7th order polynomial. Okay? So who says this is their favorite model? Raise your hand if this is your favorite model of the data. Okay. These people get really happy when they fit the data. Okay. You will make great machine learning researchers. Just joking. Okay. So who's happy with this? This is a constant polynomial. Who likes that? You like that? This is what we want our computers to do. We want our computers to be able to learn reasonable models of the data while avoiding both underfitting, if there is structure in the data that is not captured by the models, and overfitting, fitting structure in the data that is just noise. Okay? And of course, we don't know. You know, with these 8 data points, there is uncertainty. We don't know what the right answer is, but we want, similarly, our computers to be like us, not really sure about these things. Now, this model selection problem is not just limited to polynomials. It runs through all of machine learning. So, as examples, how many clusters should there be in the data in k-means or mixture models like I gave before? How many clusters do you think? Maybe 3? I don't know. You know, that's a model selection question. If you're trying to do dimensionality reduction, what is the intrinsic dimensionality of some data? If you're trying to predict some variables given some inputs, are certain features or variables relevant or not for predicting that output? Okay, this happens to be like Japanese bond prices. You know, probably lots of people in finance are interested in figuring out which variables reliably predict Japanese bond prices. Okay, that's feature or variable selection. If you're trying to model a dynamical system, like measurements from some temporal process, what order should your dynamical system have? Okay, if you're doing sequence modeling with a hidden Markov model, how many hidden states should your hidden Markov model have? If you're trying to do blind source separation with a model like independent components analysis, how many independent sources should you have? If you're trying to fit a graphical model to data, what should the structure of that graph be? And don't worry if you're not familiar with all of these things, but just as examples, everywhere we look in machine learning, there are these questions of model selection. Okay. And I'm tempted to, at some point, take a very quick break. I don't know if that's, but not now. Okay. I'll take it at the end. All right. Okay, so how do we deal with this model selection question? Well, the good news is, as I've hinted before, everything follows from the sum and product rule. So let's see how the sum and product rule can help us answer model selection questions. So now, consider that we're comparing different model classes M and M prime, maybe 2 and 3 Gaussians, or second and third order polynomial, whatever that M and M prime are. And we have some data D. Well, Bayes' rule tells us that the posterior probability of the model class given the data is this term in red, which is called the marginal likelihood, times the prior over the model class, divided by a normalizing constant. Now, the interesting thing is that people are usually afraid of overfitting, right? They're afraid that this horribly complicated model will have very high posterior probability given their data, okay? But I'm going to explain how the marginal likelihood actually automatically encodes something known as Bayesian Occam's razor, a sort of preference for simple descriptions of what's happening in the data. So here is the marginal likelihood, the probability of the data given the model class. And by the sum and product rule, that's the integral of the likelihood times the prior, integrated over the parameters. There's no other way. I mean, you can't say it's the integral of the likelihood times the posterior or something like that. That wouldn't satisfy the sum and product rule. Okay, it's the integral of the likelihood under the prior. Okay, so now this marginal likelihood is sometimes also called the integrated likelihood or the evidence. Remember, it's very different from the maximum likelihood. When I'm doing maximum likelihood, I'm optimizing this guy. And then clearly, if I optimize the likelihood and I have 8 parameters for 8 data points, I get a very, very high likelihood. Okay? So the maximum likelihood has a preference for more complicated models. The marginal likelihood does not necessarily have a preference for more complicated models. So here's how we can interpret this expression here. There are 3 different verbal ways of describing this mathematical expression. Here's one way. It's the probability that randomly selected parameters from the prior would have generated your observed data set. Okay? This is a bad way of approximating this integral, but one way of approximating it would be randomly draw parameters from your prior and then compute the likelihood for each such parameter and average. That's an unbiased estimator of this integral. Now, conceptually, if you think about that, now I have this picture here. I have 8 different coefficients. Sorry, it's a 7th order polynomial plus a bias term. So 8 different parameters. If I randomly draw those from some interval, say the uniform interval between -1 and 1, then I'm going to generate lots and lots of crazy polynomials. Okay? And very few of them are going to fall anywhere near the data. So the marginal likelihood for the 7th order polynomial is going to be very, very low, in fact, even though the maximum likelihood is very, very high. Whereas if I randomly draw quadratics, there is a higher chance that I will happen to hit something that's near the data for similarly chosen priors. Okay, so the second interpretation is the probability of the data under the model averaging over all possible parameter values. That's the same as this expression. If you like information theory, log base 2 of 1 over the marginal likelihood is the number of bits of surprise at observing data D under model M. So this is the formal definition of surprise in information theory. Entropy is expected surprise. Surprise is measured in bits, okay, in case you didn't know. And this is the surprise at observing data D under model M. Now, in fact, the conceptual way of thinking about this is that if I have some data, let's say I have some data set with n data points, I could put down all of my possible data sets that I could observe on some one-dimensional axis. This is just a conceptual drawing. And now I observe a particular data set. Okay? And I might have different kinds of models. I might have some simple models like the linear polynomial that has very few parameters. So what does that really mean? What that really means is that it puts most of its probability mass, so because this is a probability, a model is a probability distribution over possible data sets, right? So a model assigns probability mass on this axis. So a simple model puts most of its probability mass on simple-looking data sets, okay? Linear-looking data sets, let's say in that example. A very complicated model, on the other hand, spreads its probability mass over many, many different kinds of wildly different-looking data sets. But because this is a probability distribution, the integral under all of these curves is 1, okay? So if you're a complicated model, you can spread your bets over many different data sets, but at the cost of not modeling a simple data set as well as a simple model. So then when you observe a particular data set, you can both reject models for being too simple and reject models for being too complicated. Okay? So here is the same polynomial example as I showed you before with the same 8 data points. And now the green curves are showing you samples from the posterior over polynomials for each of these different orders of polynomials, where I chose the prior to be Gaussian. You know, you can change the choices. The story, the general story doesn't change. The sort of shapes of the plots might change a bit. And this curve here shows you the model evidence, in this case normalized, over the different model classes. And basically what it says is that constant is sensible, linear is not so good, quadratic is the most plausible, cubic is okay, and these are, it's sort of, you can't really see them on this, but there is some very small probability associated with these higher order polynomials. So I can show you a demo of that. You can ask me some questions if you want. Okay, so here's just a random draw. Again, this is the data I drew at random, and in this case, it says constant is the most plausible explanation of this data for this small data set. Okay. Yep. Questions?
When you look at your polynomial, it looks like that.
Sorry.
When you look at your polynomial, again.
Yep.
Polynomial, all these three lines are very close to these points, right?
Which one are you saying? This one?
And
2. Quadratic. Yeah.
Yeah, first of all, I wonder why in these pictures all these quadratics seems to be very similar and not shifted around.
This is the posterior over quadratics. Okay, so this is conditioned on the data. These are 20 samples of quadratics that have reasonably high probability given the data. So if I showed you samples from the prior, you would have quadratics going up and quadratics going down and maybe shifted around a bit. It also depends on the prior that I'm choosing, but prior is relatively innocuous here. Okay, so here is with 20 data points, and these probabilities are now quite small, and with 20 data points, it seems quite confident that quadratic is a good fit. Okay? So it's Bayesian model comparison. All of this could be critiqued. Okay. You could say, well, what about your prior? If you chose a different prior, well, you would get a slightly different picture. But you would still get this Occam's razor effect coming in to some extent. Okay? The concepts are the same. Yep.
For the right comparison, do you actually compute the integral?
So in this case, I can compute all the integrals analytically, because polynomials are linear in the parameters, and if I choose Gaussian priors and a Gaussian noise model, then I can compute all the integrals analytically. I'm also integrating over the noise variance, because that's another parameter that's inferred from the data. Yep?
Would normalizing the marginal lactose correspond to getting some kind of prior over the models?
Yeah, so this would be if I had a uniform prior over my models 0 through 5, then this would be the posterior over the models. Yeah. Any other questions? Okay. Okay. Let's take a 5-minute break. Okay, but literally 5 minutes. Okay? So 5 minutes is the amount of time it takes you to get out of your seat and get back into your seat. So 5-minute break. Talk amongst yourselves, get some fresh air. And I will start in 5 minutes, even if everybody's still walking into the room.
Question of the past.
Sure, yeah, you can.
I don't understand the difference between putting a prior on the parameter and why not putting a prior on the model.
for models that favors it. Like I can say I prefer. Okay, testing, testing. I'm going to speak. I'm about to start. I'm about to start. All right. Okay. Any questions while you were enjoying fresh air and drinks and things like that? Any questions? Any questions? People are coming in. Okay, so what I'm going to talk about is a little bit, maybe 10 minutes about choosing priors, and maybe 15 minutes about inference. Okay? So there are various schools of thought for how you should choose priors. Okay? Because people get stuck on this. And after a while, if you sort of get used to it, you don't even, you don't even think about the difference between the prior and the rest of the model. It's just parts of a model. Okay? But there are various schools of thought. There is the objective Bayes framework, where I'll explain each of these in one slide. Objective Bayes uses generally non-informative priors that attempt to capture some form of ignorance and tend to have good frequentist properties. So objective Bayes tries to look at the frequentist properties of the priors that you choose. Frequentist, by the way, is just classical statistics. Most of statistics that you would learn would be divided up into frequentist and Bayesian. Bayesian would be taught as an advanced topic, and frequentist would be taught as the sort of the regular topic. Bizarrely, because I think even high school students can understand Bayesian statistics, whereas I can't understand frequentist statistics. It's a bit weird. No, I mean it's really very beautiful, but it requires a different way of thinking about modeling and looking at the properties of models. Okay. So then subjective priors captures the idea that priors should capture our beliefs as well as possible. Hierarchical priors just represents, these are not mutually exclusive, by the way. Hierarchical priors represents the idea that, you might have some parameters and then you want to put a prior and you have hyperparameters, so you need to put a prior in those hyperparameters, and you might have to go up 2 or 3 levels in this hierarchy generally. Empirical priors or empirical Bayes says, well, at some level, some of these hyperparameters, I don't know how to set them, so I'm going to learn them by optimizing them to the data. So one slide roughly each on these different schools of thought. Here's objective priors. So non-informative priors, imagine that you're trying to do prior inference on a Gaussian with mean mu and variance sigma squared. The parameter mu informs the location of the data. So you might want to pick a prior which doesn't capture any information about location. So what does that actually mean? That means the prior on mu should equal the prior on mu minus a for all a. That's a little bit problematic, okay? Because on the real line, that implies a uniform distribution on the real line, which is an improper prior. That thing, that integral basically, that just puts zero mass everywhere, essentially. Now, people do somehow do this anyway, and the inferences that you get afterwards, after you observe some data, they become proper, okay? But the marginal likelihoods you compute are still nonsensical. The marginal likelihoods are not actually valid. Similarly, sigma informs the scale of the data, and you could pick a prior on the scale, which is roughly 1 over sigma, and similar arguments hold for that. The problems with these sorts of non-informative priors is that it's hard or impossible to generalize to all parameters of a complicated model. You can do this kind of game with a single Gaussian, but if you have a big complicated model, it's hard to say what you want to be non-informative about. Sometimes when you're non-informative about these parameters, you become very informative about those parameters and so on. And also, you end up with incoherent inferences, sort of violations of basic rules of probability theory, paradoxes, sometimes improper posteriors. It's just a mess, okay? And there are people who try to do this, but I think it's very confusing. It's better to just stick to classical frequentist theory, I would say, and then use the formal tools of that framework to understand your methods. There's nice ideas involving reference priors. So the idea of reference prior captures this notion of non-informativeness. So given a model P of x given theta, we wish to find a prior on theta such that an experiment involving observing x is expected to provide the most information about theta. So what does that mean? That means we want the prior to provide as little information as possible and the data to provide as much information as possible about theta. And this is an interesting principle. You can actually write down information gain, this sort of, this is the entropy that you have in the parameters before observing data. And as I hope you all know, entropy is a measure of uncertainty. And the reduction in entropy is information. So a bit is a reduction in entropy of sort of 1/2, okay? Now, this is the entropy before observing the data, minus this is the entropy after observing the data, averaging over all possible data you could have observed because we don't know what data we've observed. So now this is an objective function that gives us the information about theta given x. And now what we're trying to do is we are trying to maximize the information in theta from x. So we write down a system of equations and we try to solve for the prior. It's quite cool. Mathematically, it's a very interesting idea. But it's very hard to compute in general, what the reference prior is for a particular model. And the other problem that I'm troubled by is the prior depends on the size of the data set that you're going to assume. So, you can have a reference prior for data sets of size 5, but you get a different reference prior if you're now thinking of data sets of size 10, okay? But before you observe any data, you don't know how much data you're going to observe, right? So it seems a weird way of choosing priors. There's, I'll skip over this, a very classic idea is Jeffrey's prior. It's motivated by invariance arguments. You want to choose priors that should not depend on the parametrization, and it gives us sort of a framework for choosing priors. This is the sort of school of thought, I'll just be honest, this is a school of thought that I find myself most comfortable with, and that's just to embrace subjectivity. Okay, we're not modeling, to me, is never going to be objective. Your data is your data, that's objective. But if you're trying to make any kind of prediction or decision based on the data, you have to put in some assumptions. And the Bayesian framework says, put in some assumptions from somewhere, and my view is, well, try to capture your beliefs or whoever the expert is on this particular problem's beliefs as well as possible. And otherwise, it's not really coherent. Okay. Now, the question is, how do we know our beliefs? Well, this is a difficult problem. You know, you could start by thinking about the problem domain. You know, if you're trying to solve this problem, you think about the domain. Then if you start with a prior and you don't know whether it was a good prior or not, before you observe the data, what you can do is you can simulate data from the model, because it's a probabilistic model. You can generate, you know, pseudo images or pseudo speech or pseudo whatever kind of data you want. And then you can look at that data and you can say, does that look horrible, or does it capture roughly what I think my data is going to look like? And you can try to change your prior so that it matches your expectations. Now, in general, I feel like even vague priors can be very useful. And since the data will concentrate the posterior around reasonable models, that's the whole asymptotic consensus and convergence ideas. Yeah?
For general types of data, is there a way to compare synthetic data with the real one? Because, for example, for head-tail or tail variables, it's so hard to
Yeah,
just look at and decide.
this is excellent question. So it's the question is, how do you compare synthetic data with real data? And usually what people do is they design test statistics for various properties of the data, and you see whether the test statistics of the real data are significantly different from those of the synthetic data. A different way of doing that is to look at two-sample tests. And there's a great work by people at the Max Planck Institute here and elsewhere on kernel two-sample testing. And that's something that we've been using, for example, to compare synthetic data and real data. That's an actual paper that we've worked on. Okay, so something I want to emphasize, like in my view at least, the key ingredient of Bayesian methods is not the prior, okay? The prior is just where we start. We have to start from writing down assumptions. The key ingredient is the idea of averaging over different possibilities. Yep. Question? Question from the trees. Yes.
Is it coming? Can you hear me?
Yes.
Yeah. Hi, thanks. So the two methods, the methods you just described, sounded like frequentist methods to test the difference between the generated data and like what you'd expect.
Yes.
Are there Bayesian ways of doing this?
Yes.
And have I correctly thought that it's frequentist what you described?
Yes. The methods I described for comparing data sets are frequentist methods, which are very useful in this context. I tried writing a paper on Bayesian two-sample testing, but it got rejected from NIPS many years ago, and I gave up. But you can still find it on the web. There are better papers on Bayesian two-sample testing out there now as well. So it's possible to do this comparison in a Bayesian framework, but it's very difficult. And in the frequentist framework, it's very simple. Okay? So this is one setting where it's just actually a lot easier to be a frequentist. Okay. All right. Okay, so here is empirical Bayes. Empirical Bayes just basically says, I have some hyperparameters. I estimate them from data by optimizing. And the advantages of that is that it's usually generally quite robust, and it overcomes some misspecification of the priors. The disadvantage is that you're double counting the data. You're using the data both to do your posterior inference and to set your hyperparameters, and so you can get a little bit of overfitting. There is a class of distributions that lends itself to very nice priors. These are called the exponential family of distributions. The exponential family includes many of the distributions you're familiar with, like the Gaussian distribution, Poisson, Bernoulli, gamma, et cetera, et cetera. Most of the distributions you're familiar with are exponential family distributions. They can be written in this particular general form where the data and the parameters interact inside an exponent through a dot product. And it's the dot product of a vector of what's called natural parameters and a vector of what's called sufficient statistics of the data. In general, any distribution that has sufficient statistics is an exponential family distribution, sort of with very few exceptions. Now, if you have an exponential family, then there is such a thing called as a conjugate prior, which has this form. It's a prior on theta, and it has the form of this distribution, except now this is a distribution on theta. And the, the good news about that is that when I multiply this prior by this exponential family likelihood, the posterior that I get, and ignore all the math, you can look at this later, is exactly of the same form as the prior. So this is the concept of conjugacy. My prior and my posterior are in the same form when I multiply it by the likelihood. And that just means that when I have models with exponential families, life is a lot easier if I use conjugate priors. Okay, it's a computational reason for using conjugate priors. Okay, so here again is an exercise you could go and do afterwards, maybe talk to a friend about it. Consider a logistic regression model, which looks like this. It's just trying to do binary classification of some y given x through a logistic model with this dot product. And the parameters are the parameters w and the coefficient b of the bias. And it's a typical neuron of an old-fashioned neural network before people started switching to ReLUs and things like that with the sigmoid, okay? Now, so the exercise is think about priors on W and B. Like what happens if you do various things, and, you know, can you think of what's a good prior and a bad prior in this case? It's actually quite subtle when you think about it. It's not super easy. But it's an interesting exercise. So I won't go into it right now because I want to get to other topics. But I will tell you a brief tutorial on how to choose stupid priors. Okay? So here's how to choose bad priors. Choose an improper or uninformative prior so that your marginal likelihoods are meaningless. Okay, that's one thing you could do. Alternately, you could be very dogmatic and choose very narrow priors that can't adapt to the data. You could choose priors that are very hard to compute with. Okay, might be a sensible prior, but you know, you've just created yourself a big computational problem. Then after choosing your prior, don't sample from your model to see whether simulated data makes sense or not. And in fact, many, many times I will talk to people who try to do Bayesian inference, and they say, this is the model that I'm using, and I say, well, you know, have you simulated from your prior? And they look at me like, oh, that's an interesting idea. I just thought I'd just, you know, crank through the handle. And I'm like, no, no, no. Your prior means something. Your prior is a statement about the kinds of data you expect to see. So before you actually see the data, just try to simulate from your model and see what happens. Okay? Never question your prior. Don't describe your prior in your paper so that your work is not reproducible. I mean, that's also a good tip. Okay. All right. So, so here is the, you know, the basics. And in the last few minutes, what I want to do is give you a whirlwind tour, because that's all the time I have left. But I think this has been good at the pace with all the questions. I think that's the right idea. I want to give you a whirlwind tour of the key computational problems in Bayesian inference. These are generally involving averaging over parameters, like these integrals here. Okay? So computing marginal likelihoods can be computationally intractable. So here is a, you know, imagine you have a situation where you have some observed data y, you have a model with hidden variables x, and some parameters theta, and some model class m, and now you want to compute the marginal likelihood. Before I was calling it P of d given m, but now I'm distinguishing between some observed variables and some hidden variables. So it's P of y given m, and I'm having to integrate over the parameters. And if I have hidden variables, then the presence of these hidden variables results in a double integral. I have to integrate over not only the parameters, but these hidden variables in my model. And you might ask, what's the difference between parameters and hidden variables? Well, actually, they're both unknowns, right? Things you don't know. But generally, hidden variables are, the number of hidden variables is something that would grow normally with the amount of data that you have. Like, for example, if you have medical records, then the disease state, the symptoms of each patient would be the observed variables. Maybe the disease state of each patient would be the hidden variables that you're trying to infer. And the model that maps from disease state to symptoms would have some parameters theta. So x's will grow as you have more and more patient, because each patient has its own disease states. Okay? So the presence of latent variables results in additional dimensions that need to be integrated or summed out. And the likelihood terms can be complicated. So that's the bad news. Okay? The good news is that there are many, many methods for doing this approximate integration, including just do optimization and treat it like approximate integration. So I'm going to try to give you a flavor of maybe 2 or 3 of these. Maybe the first 2. We take a couple of questions, and then in the next lecture, I'll talk about the rest. Okay. So here is a Laplace approximation. And I'm going to talk about doing these things in terms of computing the marginal likelihood. But it turns out that computing the posterior is sort of, they compute the posterior as a side effect as well. Posterior over the parameters given the data. So imagine you have a data set y, you have some models m with some parameters theta, and what you want to do is you want to compute this marginal likelihood, this term in red. Now, it turns out for large amounts of data relative to the number of parameters, where d is going to be the dimensionality of the parameter space, the parameter posterior is approximately Gaussian around the maximum a posteriori estimate, map estimate theta hat, under certain regularity conditions. Okay? This is well-behaved, identifiable models that are finite dimensional. D is, in fact, the dimension here. But in general, it's true that the posterior is going to converge to a Gaussian. You could see that in the coin toss example. That posterior, even though it was never actually Gaussian, was looking more and more Gaussian after a while. Okay? So this is the form of the Gaussian. The mean is around the map estimate. And this covariance matrix of that Gaussian is a d by d Hessian matrix, where the elements are the second derivatives of the log posterior with respect to the parameters theta I and theta j. Okay, these are the elements of this d by d matrix. Okay? I won't go into the details of where this came from. This is a sort of instance of something called Bernstein-von Mises theorems in Bayesian statistics. Okay, so now it's true that I can just rewrite the joint as the marginal likelihood times the posterior. So by taking this term over here, the marginal likelihood is the joint distribution divided by the posterior. So now what I'm going to do is I'm going to take the log of the marginal likelihood, and that's going to be the log of the joint divided by the log of minus the log of the posterior. And I'm going to plug in this approximation for the posterior. And then I get this term here. This is the log of the numerator here. And then in the denominator, when I evaluate this expression at theta hat, all terms fall out except for these things. Okay, so this is nice because this says my log marginal likelihood is approximately my log prior plus my log likelihood plus a penalty term. That penalty term is d over 2 log pi. So this thing, for large data sets, this thing doesn't really matter very much. Minus 1/2 log of the determinant of that Hessian matrix. So I can do optimization to find theta hat, And then around there, if I approximate my Hessian and I compute the determinant of the Hessian, that is like a regularizer. That's a penalty term that I apply to my log posterior to approximate my log marginal likelihood. Okay, so that's called Laplace approximation. The Bayesian information criterion basically takes that and drops all terms that don't grow with n. And what you get is that the log marginal likelihood is the log likelihood approximately minus d, number of parameters, over 2 log number of data points. Super easy to compute. This is also sometimes called the minimum description length criterion. You just do maximum likelihood and you penalize by number of parameters over 2 log n. That happens to be an approximation to the log marginal likelihood. Okay, I'm going to stop there. I'd like to see if there are any couple of questions, and then we'll continue tomorrow. Yeah. Question.
The determinant of A you had on the previous slide, is this also the Fisher information, or is this something different?
Yes, it's related to the Fisher information matrix. Yeah.
Okay.
Yeah.
That's expectation, not.
Yeah. Yes.
Isn't this approximation some kind of like simple secondary Taylor?
Yeah. The other way of deriving this is as a Taylor expansion. Yeah. This is a second order Taylor expansion of the log likelihood. Sorry, of the log posterior around the mode. Yeah.
The observation I was just calling again.
Yes.
For picking a prior, is it very weird to divide my data to 2 parts? Use the first part and find a maximum entropy distribution which makes the least sustainable distribution. Use that as a prior and use the rest of the data for doing Bayesian inference. Is it very weird or it's something?
It's not very weird. There is a whole conference called Maximum Entropy and Bayesian Methods where people do things like this. There's some. It probably would work quite well, except that it's slightly inefficient to just use half your data. I mean, you could imagine doing even less of your data and using a maximum entropy method on a smaller amount of your data. It's a little bit arbitrary in the sense that you're trying to be somewhat objective by doing that. And there's no single way of doing it. But yeah, it's not a bad idea in practice to do that. The purist would say that you're not really being coherent under any single prior when you do that. But maybe you don't care. Maybe you get good performance anyway. Yeah. Yeah.
So you said when you do empirical base and you fit your prior to your data,
Yep.
then you fit your maximum likelihood to the data as well. You said you overfit slightly, right? Don't you overfit a lot?
Okay, good question. So when you do empirical Bayes, what you generally do is usually models have lots of parameters, okay? And so what an empirical Bayes procedure does is it tries to be as Bayesian as possible over those lots of parameters. But then there's a few hyperparameters, like maybe 3 or 4, that you don't know what to do with. So you optimize those. This is sometimes why it's called level 2 maximum likelihood. Level 2 is the level of the hyperparameters. Now, often it turns out that those hyperparameters don't control exactly what your model is doing. They just control general properties of the parameters. So it's very hard to overfit a lot just by fitting these 2 or 3 parameters. A beautiful case of this is with Gaussian processes, where the standard textbook just says do type 2 maximum likelihood and it works okay. And most people find that for most applications it works well. The purist Bayesian wouldn't like it, but it's just computationally easier. Yep.
On the slide where you have Laplace approximation and a lot of methods, how do you decide when you have a problem which to use when?
Beautiful, wonderful question. Okay, so in classical machine learning, you have usually an optimization problem. There are many different optimization algorithms you can use. And you can ask your friend which one worked best, basically. Or you try them out and you see how well they work. In Bayesian methods, it's not optimization we're trying to do, it's integration we're trying to do. So again, a lot of it is unfortunately cultural. So in statistics, people like Markov chain Monte Carlo, but very few people in statistics use expectation propagation because it came out of the machine learning literature. So some of this is cultural, but this is just a statement of fact. If you're trying to be rational, then what you consider is that these methods all live on a particular speed-accuracy trade-off curve, okay? So some methods are more computationally expensive, but will eventually give you more accurate answers. And some methods are very fast and cheap, but won't give you very accurate answers. So it's hard to know exactly where everything lies on that speed-accuracy trade-off, but I would be safe to say that BIC out of all of these is the cheapest method, because it just involves doing maximization plus a penalty that you can compute in a couple of floating point operations. And you compromise on the accuracy. At the other extreme, MCMC is an anytime algorithm, which means you can run it for as long as you want. And if you want to prove that it's converged, you will run it for a very, very long amount of time. But actually, you can think about the amount with which you run MCMC as simply a speed accuracy trade-off parameter. But it's an excellent question.